As serious of a problem as pollution is, it could be either made better or worse depending on the weather and the topography of the region. We're going to look in this video at a couple of examples of how weather and topography can affect pollution. So, the first factor that we're going to look at is the role of dilution through wind. So, here in the figure on the left, you have a bunch of pollution. Sorry, I need my pen. There we go. You have a bunch of pollution here in a smokestack. If the wind is really slow, then that pollution just kind of hangs out here. It doesn't go very far. Whereas in the figure on the right, if the wind speed is higher, then that pollution, really starts to disperse and it becomes less dilute. And so slower wind speeds allow pollution to build up, whereas higher wind speeds cause it to spread out. Now, many of you might think, but if you're just spreading out the pollution, then you're just spreading out the problem. No. Remember what pollution is. Pollution is a chemical where if the concentrations are high enough, it causes health problems. When it disperses like you do in the right figure, then the concentrations become smaller, and so it actually becomes less harmful. And so the figure on the right is definitely more of an ideal circumstance. Now, what about the stability of the atmosphere and inversions? Well, the stability of the atmosphere has a huge role. If you have this figure on the top, figure A here, you have an unstable atmosphere where the upper atmosphere is cooler, the lower atmosphere is warmer. So you get a parcel of air, it rises, its temperature stays warmer and warmer than the atmosphere around it, and so it keeps rising. Well, thankfully, pollution is hotter than the air around us most of the time. And so since it's hotter than the atmosphere around it, it's going to rise. And you say, oh, great, now we're just polluting the atmosphere. But remember that the more it can be pushed up, the more it spreads out, and it becomes more dilute, less concentrated. And if it can become less concentrated, then it's less of a worry. In fact, often when it gets up into the atmosphere that high, those pollutants, which are now just simple chemicals in the atmosphere, no longer a pollutant because their concentrations aren't high enough. They often serve as cloud condensation nuclei. And when they do, the water grabs a hold of it and then will eventually fall back to the earth harmlessly as rain. So that's the ideal. However, occasionally you get your inversion where it's cooler at the surface and warmer above. Then when you get a parcel of air and it rises and cools, it becomes colder than the atmosphere around it, so it wants to drop back down. So you have warm air pollution here. It rises, hits a layer that's actually warmer above it than it is. So it goes up, hits that warm layer, it can't go any further, it just flatlines and builds up at the top of that inversion layer. Occasionally you may have a smokestack that is high enough though. If you have a smokestack that's high enough, then yes, that pollution can penetrate through the inversion layer and allow smoke to rise and disperse and become not a problem. But for the most part, especially for these factories where smokestacks are short, the pollution is just going to hit that inversion layer and build up underneath. The figure on the left is a picture of a valley where pollution has built up significantly because of an inversion layer. In fact, the figure looks like it's not just a radiational inversion like what you have after the night. That looks like a long-term weather scale inversion. So it can really build up. In fact, where I did my studies out in the state of Utah, this is a very, very common thing. We want to talk about the mixing layer and the mixing depth. I will explain those a little bit more in the next slide right here. So sometimes you may have something called a subsidence inversion. What happens here is the sun heats up the surface enough that you do get an unstable layer right near the surface. But if you have, say, a high pressure system sitting over you, that causes air to sink from above. And so you have air that is subsiding or sinking. So that's why it's called a subsidence inversion. Often when that happens, you get warm, dry air sitting on top, pushing the cold air down on bottom, and so you end up with an inversion. So it's hotter above and cooler beneath. So even though down here at the surface it's unstable, it's extremely stable up here. So let me clarify it this way. So here we're saying it's stable because of the inversion, but down here it's unstable. As a result, your pollution, wherever it forms, goes up because of its instability, hits the stable layer, and flatlines. It just spreads out right underneath that inversion layer. The depth of that unstable layer is known as the mixing depth. In other words, because of the rising motion, all your air is going to mix. So the mixing depth is the actual height. The layer itself is called the mixing layer. So throughout that whole mixing layer, you do have your chemicals that can mix around and disperse and become less concentrated, but because of the substance inversion, it can't mix very far, very high. And so after an amount of time, eventually there's no way you can disperse the pollution enough to make it not harmful, and you end up building your concentration of pollution really high, even in this unstable mixing layer. So how can topography affect pollution? Well, remember that throughout the day, air rises up mountain slopes, but at night, when the air on top of the mountain gets colder, that air is going to sink. And any pollution that is found at the tops of the mountains, well, they get caught along with that downdraft, and the pollutants build up here in the valleys. And that can really increase pollutant concentrations. Cities like Denver and Los Angeles, Salt Lake City, Pittsburgh are very, very famous for this. They get lots of topographical air pollution problems.